Okay, so one last review before we do probability tests tomorrow. There's several kinds of probabilities. I just want to go through them really quick. Why would you ever use blanks? You'd use blanks if you're trying to take a list of books. Let's say that there's 1, 2, 3, 4, 5 books that I could put on this shelf, and they want to know how many different ways they could be put on the shelf. Well, this is a permutation question because it's like how many different orders they could be in. Because I'm going to put all the books out on the shelf. It's just what orders they'll be in. So I could put like book A, book B, book C, book D, book E. I could reverse that order completely and start with E, etc. So in this kind of problem, you got to think, what are my choices? How many choices do I have for this spot? 5. How many choices do I have for this spot? Well, there's only 4 because I used one up over here. So there's 5 times 4 times 3 times 2 times 1. I'd want to remind you that on the calculator there's a thing called a factorial. 5 factorial would have answered this question. It's under number. It's under math, and then probability. You look for the little exclamation mark. All right. So if I also use these blanks on license plate questions where it's like how many different license plates could have 3 letters and 3 numbers. Well, you go, there's 26 letters, 26 letters, 26 letters, and 3 numbers, 10, 10, and 10. Why 10? Because it's 1 through 9 plus also 0. All right, so what if I change this around and say, but you can only use the letter, you can't use the letter W in front because that's a whiskey plate. And you're not, if you have a whiskey plate, that means that you have a, like 3 DWIs, and so they make you have a plate that starts with W. And so you don't want the plate that starts with W. So then, if that's not one of the options for a license plate, then there's only 25 choices for that. All right, so then all the license plates out there would be 25 times 26 times 26. All right, so what if they made it into not lining up books, but lining up kids? Let's say that there's a whole bunch of elementary schoolers, but there's this one girl who's just paranoid about being in the front of the line, and so they don't want, she doesn't want to be in the front of the line. So then there's these 6 kids, but only 5 of them could be here. But she'll be in the second spot. That'd be all right. All right, so now how many choices do I have for this spot? You would think it would be 4 choices, but I really have 5 because that girl who wouldn't be in the front now would be able to be here plus 4 other kids. So that's a 5 times 5 times 4 times 3 times 2 times 1. All right, so the blanks are really good if you can repeat things like in license plates, because a permutation can't handle repeating. And it's also good if you're going to fix something like a kid can't be first in line or a kid must be last in line. The blanks are good for that. All right, another kind of probability is binomial. Let's say I had a kid who's a 95% free throw shooter, and I want to see, they have 4 shots at the end of the game, and I want to see what's the probability they make 4 out of 4 if they are a 95% free throw shooter. That one's actually too easy because you probably could do that one in your head. I'm going to say what's the probability they make 3 out of 4 shots? And it would go like this. A C in the front and 2 sets of parentheses. And this is make and this is miss. And I would say I have 4 shots and I want to make 3. The make percent is 95%. The miss is 5%. And then the 3 here gets copied up to here. Whatever number is here goes there. And then these 2 numbers together have to add up to my total number of shots. So this has to be a 1. All right, so that's how I would do my my binomial. Another example of a binomial is, let's say that somebody's going to have 7 kids in their family. And what's the and let's say that it's a 50-50 chance of boy and girl. What's the probability they're going to have 6 boys and 1 girl? And that can be in any order. All right, so then you'd go C, parenthesis, parenthesis, and if I have 7 kids choosing to have how many boys? 6 boys. And this is boys, so this boys goes here. This number always goes right there. And then the boy percent was 0.5, the girl is 0.5, and then these 2 have to add up to 7, so that would have to be a 1. All right, so that's my probability of getting 6 boys and 1 girl. All right, moving on. There's another kind of probability, and it's actually not even a probability, it's just a P or a C. Use P when order matters, and C when it does not. So here's an example. Order matters when you're in a race, and order does not matter when you're on a committee. Anytime you're asked about like finishing first, second, or third place, you're doing a P. Anytime you're just picking out a group, it's a C. So if I did a race with 30 kids and I was going to give out first and second place, that would be a race, so I can tell right away it must be a P, and there'd be 30 P2. Those can be done on the calculator under Math button and the PRB, and then you look for the thing that says NPR. Just like that is the committees kind of question or little groups. Let's say that there's a group of trolls. You got 8 trolls, and there's going to be the troll convention, and so they need to pick 2 of their comrades to go to the troll convention out in the cave down the way. So they have 8 they can choose from, C2, and now I've got my number of little groups of trolls that I could pick out of my 8 troll collection. All right. Moving on, let's say I was going to do expected value. There's a couple expected value things you got to remember. One is P times A, then add. You'll notice that pretty much any problem that you do with expected value has a probability and then an amount, and then you add them all up. Okay, so let's say there's this spinner that you could spin, and you get 10 bucks if you go here, you get nothing if you're there, and you get 100 bucks if you go here. So you really want that one, of course. Let's say that there's a 10% chance of hitting this one, obviously a 50% chance on the spinner hits that one, and then this must be a 40% chance of hitting this one. What's this game worth to play? I would easily pay $5 to play this game, but I wouldn't pay $90 to play this game. That wouldn't be smart at all. So something between $5 and $90 would be smart. What is it? You find the P, and you find the A, and then you add them up. What's the probability I'm going to hit this spot? 0.5. The amount I get if I hit it? 10 bucks. What's the probability to get this spot? 10%. The amount I get if I hit it? 100 bucks. And the last one is, what's the probability that I hit this little spot right here? 0.4. And what do I get if I hit it? Nothing. So I add them all up now. Or I got to multiply first, actually. 0.5 times 10 is 5 bucks. That's 10 bucks. And that's nothing. Add them all up, 15 bucks. It's worth $15 to play. So what's the expected value? $15. What happens if you pay $15 to play? Then your expected value is 0. Because you're expecting to win 15 bucks, but you paid 15 bucks to play, so you're going to win nothing. So if they tell you an amount, you got to subtract that then to see how much your expected value is. So if they said it costs $15 to play, then your expected value would be 15 minus the 15, nothing. This is what it was worth to play. All right, another expected value is life insurance. So let's say that you buy a life insurance policy. You either live or you die. And let's say that your chances of living are 95% chances of dying, 5% chance of dying. And this is the probability. The amount you get, well, it's kind of not really you, it's your family would get if you die. Let's say that you bought a $1 million policy. And people do that all the time. Because if they die, they want to be able to have their kids still be able to go to college and stuff without them there to pay for it. So that's the amount you get if you die. If you live, you get nothing. Then, under this scenario, let's say that for your $1 million life insurance policy, it costs you $3,000 for the year to buy this policy. All right, so then your probability times your amount here is 0 because you times it by 0. Your amount here, let me see if I can do the math quick in my head, 5, and then I move the decimal over. I would normally have 1, 2, 3, 4, 5, 6 zeros, but I take off 2 for the decimal places. So that's 50,000. See if I did that right. 10% of that would have been 100,000. So yeah, that's right. 5% of 50,000. All right. So this life insurance was really worth 50,000. So how do I figure out an expected value? Well, if it's worth 50,000 and I only had to pay 3,000 for it, I take that away from my value. Then this was actually a positive $47,000, which means that the life insurance company really shouldn't have made that deal because there was a pretty high chance I was going to die. This 5% chance is what really threw this off a little bit. So this would have an expected value for you of $47,000. You're likely to make money on it. Now, it makes some sense if you think about it. You're going to get so much money if you die, the $1 million, that you should have to pay a fair amount to be able to have that privilege. All right. So for a typical person, their chance of dying within 1 year is very small. It's probably nowhere near 5%. It's probably like half of 1% chance you're going to die this year. All right. Moving on. That was expected value. The next topic is Venn diagrams. If you have one of these, and I'm going to put some dog, cat, and a refrigerator. Kids that have a dog but not a refrigerator, that's pretty rare. Let's say there's one. Let's say there's no people that have a cat and not have a refrigerator. Most people have a fridge, so there's like 20 here. Let's say dog and cat and a refrigerator. Let's say there's 3 of those. One of these, 2 of those. Okay, and then let's say there's somebody who does not have a dog, a cat, or a refrigerator. Say there's like one of those. Then, what's the probability of a cat? That means if I picked a person, what's the probability I get a person that has a cat? Oh, wait, there's a missing number there. Say that there's one person in that zone right there. All right, well, probability always is something what you want over what's possible. What do I want? I want somebody who has a cat. That's going to be 3, 4, 5 people have a cat. You notice it's not just this one, it's this one and this one and this one. And it's 5 over what was possible. Any of these people could have been chosen, and there's a total of 22, 5, 6, 7, 8, 9, 29 people possible. So I take 5 out of 29 chance that I'll get a person with a cat. All right, the harder kind are givens. Given that the person has a dog, then what's the probability they have a refrigerator? Okay, so that's probability of fridge, F-R-I-D-G, given, I need a like straight line for that, given that they have a dog. All right, as soon as I say given they have a dog, it narrows it down to just these. And the probability that they are going to have a fridge, given the, okay, so the given is down the bottom. That tells me how many things are possible. 23, 4, 5. 25 kids were possible because they had a dog. Then what's the probability to have a fridge? The fridge people are right in here, and that's going to be 23 out of the 25. And that makes sense. It's a high probability that that would happen. All right, so when it says given, you narrow down what's possible to be only the things that are given, like the dog. Only those things are possible then. All right, next topic is contingency tables. A lot of times they'll have a table with like dog, cat, male, female. So let's say I asked kids in here, dogs and cats. Let's say the males, there were 10 guys that had a dog in their house. There was 2 guys that had a cat in their house. Females, let's say that there was 15 that had a dog in the house, and cat in the house, let's say that there's 1. So then the total number of cats that are accounted for here would be 12 households that have cats, and then there's 16 households that have dogs. Now this is one of those where they can't overlap. Yet it turns out apparently you're not allowed to have a dog and a cat, otherwise that would mess everything up. All right. So the totals here would be 25 and 3. So how many total cats are out there? People that have cats, there are 3. 2 of them are male and 1 of them is female. etc. All right, so now, what's the probability question like? It would say, here's an easy one. What's the probability that I get a kid who has a dog? Well, I'd have 12 out of 28 total people here. Yep, 28 total humans. And 12 out of 28 would be a probability of getting a person with a dog. If I said given that they have a dog, what's the probability that they're female? As soon as I said given they have a dog, I knew I was here. And it was out of 25. And probability that they're a female, that would mean what I want is on top. And that's right there, 15. So 15 out of 25. All right, those are going to be your easiest questions of the contingency tables. And the last thing is a tree. You can always draw a tree. Even on those really tough binomials, trees work for everything. Even if the numbers change from like 60-40, after they're on their second kid, maybe there's a 70-30 chance of getting a boy. Trees can handle that, and most other things can't. So trees are handy because they always can work. And on a tree, basically, let's say that the question was, what's the probability you're going to have 2 boys? Well, that's easy. This times this tells me boy, boy. And 7 times 6 is 42. And if I wanted to figure out probability of having at least 1 boy, that would mean this would be at least 1 boy. This route of boy, girl, that's at least 1 boy. Girl, boy, that's at least 1 boy. I would find all those and add them up. Why wouldn't I include this one? Because they don't have at least 1 boy. Now, if I wanted to go this plus this plus this, I could do that, or there's a faster way. If I wanted to do at least 1 boy, then I do the probability of 1 minus the one thing that I didn't want. That's another technique that works well. If you're going to have to add up a whole bunch of things, you can always do 1 minus the one thing I didn't want. All right, there's a quick summary of everything all the types of ways to solve probability questions.